Hey, Andrew.
Welcome, Andre. I make you a co-host so you can share screens, test screen sharing.
Hi. So
Hey, Andrew.
you're Yahweh, right? I'm
Yahui.
Okay.
Nice to
Your
meet you.
name correctly? Okay.
I think you can share the screen now.
Okay.
Yeah, it looks good.
Oh, is this good? Okay.
Yeah, I think everything is fine.
So what was this nice background I was seeing earlier? With the this one, yeah.
It's a Sherbrooke. Place.
Yeah, I thought I recognized it, but yeah, actually my wife worked in this hospital here to the left. And
maybe
so
you can.
Where did you take this?
Just imagine we can travel at this time. Can you tell us the mountain in the background?
Yeah, the mountains are it's in the Appalachian chain, so it's the same mountains that are in your area. They go from Gaspésia, that's the north of St. Lawrence River, all the way to Georgia. So that's this mountain chain, and in that direction, probably what we see is Mont or something like that. Yeah. So it's in the east. To the left, completely is a hospital where my wife worked for a while, and you can almost see where I used to live. I think it was somewhere to the left, where near the near some of these red trees, and to the right, this building is another hospital, and university. It's just we are on top of a hill that's called Mont Bellevue, which means nice view, and the university is just on the back of this. Yeah.
I see.
So from the university, we can walk to that spot in about 10-15 minutes. Yes.
I see.
So did you and Juven organize this series or?
Yeah. So,
Who gave you this idea?
Joey got the idea. Yeah, I think Joey initiated it.
Who? I'm sorry, I didn't hear.
I didn't work on that field, but I remember when I was a grad student at MIT, Pedro Lee and Santo, they gave some introductory seminars on HTC.
Okay.
And then I saw that this is a good timing to have that type of things. And also, it's possible we can even keep going because it seems good. The problem hasn't been solved, so maybe we can just keep going.
Okay, so it's a very nice initiative.
Yeah. Maybe you can have another seminar 10 years later to see what has changed.
And I'm curious about you. Are you faculty, postdoc, students?
We are both postdocs at Hubbard.
Okay.
Yeah. I'm working with Ashley and Subia.
Okay.
So yeah, I actually worked on cuprate.
Pardon me?
Yeah, we work on cuprates.
Yeah, I say I'm interested in cuprates.
Okay.
Yeah, so I'm quite interested in this seminar series.
Okay. Well, we'll see what you have to say about this one.
So the seminar will start maybe 10 minutes later.
Oh,
so yeah, usually we will be later, 3 minutes later, because people will come later.
Okay.
Than the official time.
Okay.
Yeah. So you can have a rest now and come back maybe at 30.
No, that's okay. I can I will just sit a little bit.
Maybe grab a cup of water, a glass of water.
Yes, I have a glass here. Well, I don't dare say, but I need some energy, so I took a little bit of Pepsi. So Ashwin is mostly working on topological materials, no?
Not too much, I think. So right now, I think one of his focuses are actually on twisted bilaterography.
Mm. Yeah. Okay. Yeah. Want to or you can with your colleagues down the road, right?
Yeah.
Yes, I was a student at MIT, and I worked with actually Professor, also with Professor Paul Martin, who was is dead now, but he was a professor at Harvard. So I did this trip from MIT to Harvard at least once a week, if not more.
I see.
I did it I started by doing it in bicycle, but then after I got killed, almost killed a couple of times by the cars.
Wow.
I decided I would use the subway or walk.
I see.
But actually, actually the bus was more convenient than the subway, turns out.
Yeah, I usually just took the subway. Yeah, so I was a PhD student at MIT. So
Okay, with whom did you work?
Center.
With Center, okay.
Yeah, so I also traveled a lot between MIT and Harvard.
Okay. So how long have you been a student? Postdoc, I'm sorry.
I'm now at the second year.
Okay.
Yeah.
Hi, John. Hi, Dieter.
Hi, André-Marie.
Hi. Alexandre. So, Dieter, are you retired now, or?
I'm officially retired, yes. I'm an emeritus, but I have the possibility just to work, and that's what I do.
Okay, very good. Do you have to retire? Is it compulsory, or?
Excuse me?
Do you have to retire? Is it compulsory?
Yes, that's we have. Yes, I prolonged it for a year, but since the conditions were so good for me to retire, I did that. I could have, in principle, prolonged for another 2 years, but then it's over. How about you? How about yourself?
I could be retired. I'm 68, but yeah, I mean, there's no obligation to retire, and as long as my brain is working and my colleagues tolerate me, I suppose.
Yes.
What I usually say is that I take care of the laws of physics and the laws of biology take care of me. So eventually the biology will win. So, but for now it's fine. Yes.
Well, good luck. I'm looking forward to your talk.
Yes, thank you. Oh, I heard a story about retirement. Actually, I don't know if it's true, but apparently Bismarck wanted to install retirement in Germany. And then he said, if people retire at a certain age and then I have to pay, how long will I have to pay? So the statisticians got to work, and then they came back to Bismarck and they said, well, by 65, they will all be dead. So Bismarck said, okay, 65 is a retirement age.
Some time ago.
Yes. Hi, Patrick.
Hey, how are you?
Okay, you.
Good to see you
Yes, good to see you.
virtually.
So yeah, we found a nice picture of Sherbrooke here.
Oh yeah.
Very beautiful.
Yes, in the fall. Unfortunately, these leaves are there for just a couple of weeks usually, but
Mhm.
the university is about, we can walk to this spot in about 10 or 15 minutes. The university is just on the other side of the hill.
Mhm.
Yeah. So as you see, it's not a very big town.
Hmm.
So it's a nice place to be during a pandemic.
Is your university open or closed?
The university has closed at the beginning of the pandemic, but not long after it opened. So, but you know, students classrooms are usually filled with like a third of the students or something, and then if you give your class the students. It has to be broadcasted as well, so students can either come or go, and then there are masks at the entrance that you can have every day, and then you can wash disinfect your hands everywhere.
Mhm.
And we had a choice to either go there or give it. So I gave everything from a distance because. Yeah, given my age, I didn't want to take too much of a chance. But I think at MIT you closed, right?
Yeah, it's completely closed.
Yeah. So I used this light board on the back here to teach.
Uh-huh.
But
So what's it called? What's the stuff you have at the back? Is it something in your home or is it in your office? This light board.
It's a light board, yeah. So the technicians made it actually from scratch, and so usually I'm on the other side, and and I have my iPhone that I use as a camera, and it does the mirror operation.
I see.
So you can face the students and write on the board.
But this is in your office, this light board.
No. This is at home. I'm at home.
Oh, so I see. So the university paid for this light board at home, or?
Pardon me?
The university paid to have that installed?
Yes. Obviously, I will return it to the university, but yeah, they paid for that. Yeah.
Oh, how much does it cost? Maybe I try to get one.
Yeah, now you can buy it, I think, in industry, but when we did it, I guess it was when the technicians did it. It had to be done, and the whole thing cost about $1,000 or something like that.
Yeah, I guess I'm looking at the online. That seems to be the price. Oh.
Yeah, the excuse me. I think in the end they took a glass that is good quality, but perhaps it could have been even better quality because it's very important. You know, it works by internal reflection, so you have LED lights everywhere around the board, and there's internal reflection, and then when you write, the light gets out. So if there are defects in you see them a lot, or the glass is rather fragile. So even with my nails, I could scratch it. So yeah, perhaps you could have paid for better quality glass, but other than that, it was great. But there's lots of technicalities with the wireless camera, and then I had two computers, one to see the students, one for me to use. And
I think we should get started though.
Yeah. Hi, Andrew. Can you share your screen again, maybe?
Yeah.
Okay. Are you ready, Andrew?
Hi, Doug.
Are you ready to start now?
Yeah, whenever you want.
Okay. Yeah, then let's start. Hello, everyone. Welcome. Today it's our great honor to have Professor André-Marie Tremblay as our speaker for the CMSA seminar series on HTC. So André is a theorist and a full professor at the University of Sherbrooke in Canada. He is mainly working on strongly correlated system with a focus on HTC cuprates. So today he will tell us about a unified theoretical perspective of the cuprate phase diagram. Welcome, André, and please.
Okay, thank you very much, Yawi, and also Juben for organizing this very nice seminar series that I learned a lot following it. And so I'd like to dedicate this talk to the late Professor Paul Martin, from whom I learned much of the basics of this this field. So I guess the first question is who ordered this? And well, I mean, what I mean is this. So it's a bad joke to start this seminar, but I do my best. So what I mean is that it's not easy to use. Well, in fact, you cannot use standard methods of solid state physics to understand it. For example, we know what an antiferromagnetic insulator is, but if you go above the Néel temperature, you have an insulator. Now, when you dope, so this is temperature, this is doping. So when you dope, you get this phase that is called a pseudogap. And here we go to a phase that has a linear resistivity and linear in temperature, that's called strange metal, and something that looks like a quantum critical point. And obviously superconductivity in the presence of very strong repulsion. This antiferromagnetism here is a sign that there are very strong repulsion. And we have competing ground states. You see a charge order here, spin-density waves, etc. And following the lead of P.W. Anderson, I guess we start with the Hubbard model that has a hopping T for nearest neighbor, T prime second nearest neighbor, and T double prime for next nearest neighbor. And I guess that if you go back to the phase diagram I showed, we can paraphrase Churchill by saying, never have so many owed so much to a single model, right? If we want to understand this whole phase diagram with this simple model is quite a challenge. So this model has a kinetic energy here with all these hopping parameters and some interaction. So if we have only these hopping parameters, then we know that this plane wave is a solution. And if we have only this repulsion, then we need to put electrons and localized on each site and avoid double occupancy. So this is a very entangled problem in the case where interactions and hopping are comparable. And in fact, there may be a phase transition in between. So in the strong large U limit, when we are at half filled, an effective model is the Heisenberg model to describe this. In fact, it's a charge transfer insulator, and I will come back to this later. So there's a big difference between doping a semiconductor and doping a Mott Hubbard insulator. So if we look at a semiconductor, it has a conduction, a valence band. And if we have n orbitals here for this valence band. There are two end states. And in the conduction band here that I take as empty, there are two end states. And doping just means shifting the chemical potential. Now, if we look at the Mott-Hubbard case, there are there's a single band here, so there's two end states, but n of them, these correspond to just removing an electron here, and n of them correspond to adding an electron on an already occupied site. So then when you dope this model, you see that you lose one state here and one state there, and you get two close to the Fermi level. So we rearrange this. So now this can be seen by X-ray absorption, and that's I'm showing you an old experiment here. So if we take the high energy photon, you see, and take a core level and take the electron just near the Fermi surface, then this is zero doping. So this is this curve here. We get absorption at that photon energy. Now, if we take the same compound, but well, we dope it, it's not exactly the same compound, it's doped. Then what happens is that you can still go there, but there are fewer states there. So for example, with 2% doping here, this has gone down. And there's now two states near the Fermi level, so you get another peak here. And this peak should grow twice as fast as this one goes down. And you see that indeed, this has gone down like this and up like this. So let me do a little movie of this. So that's it. So you see that it's a dope Mott Insulator for quite a while. So the take-home messages in this talk will be that most of the main features of the phase diagram follow from the Hubbard model, and that this physics is continuously connected to the Mott transition at affily, and that we need to look beyond the traditional tools of solid-state physics to work this out. So I'll talk first about the method. I'll spend a lot of time actually on the method. And then I'll discuss the one-band model, both the pseudogap, the quantum critical point, and the D-wave superconductivity. And finally, the three-band model with the pseudogap and the D-wave superconductivity. So the method. Let me talk about the precursors first. So there's the many-body problem is very complicated. Obviously, the Hilbert space here is 4 to the, for example, with n sites, there are 4 states on each. So empty, doubly occupied, and singularly occupied up down. So we have 4 to the n Hilbert space. And so that's not only for the Hubbard model, that's all the time. So the many-body problem was simplified a lot by the Hohenberg-Kohn theorem, who showed that the ground state energy is a functional of the density and the local density. And that led to the idea of exchange correlation. And then Kohn and Sham suggested to represent this density on a single particle state that becomes a basis state for further calculation. And then that's density functional theory that's extremely successful to describe the top rows of the periodic table, materials made with top rows of the periodic table. Now this assumes that the density is varying. I mean, it's valid in general, but it's very hard to find the exchange correlation functional that takes into account very sharp variations of the density, like we see when we have the localized d orbitals. So we need to take into account both this localized aspect and the delocalized, and that takes us to the method I will be using. So again, there's a basic idea, and the basic idea is due to Metzner and Bohart, that the in an infinite dimension, the self-energy is a function only of the frequency. In other words, it's local. Then Antoine Georges and Gaby Cotillard used this idea to devise what has become under the name of dynamical mean field theory, with contributions from Jarrell as well. So what is this approach? I mean, I will talk now immediately about cluster generalization of this approach. Okay. Once, I mean, the method I will describe here, once we have something we believe is the right solution, I think it's useful to compare with analytic approaches like has been done here by Subir and so on. But here I will focus only on this dynamical mean field approach. So the idea is to make the localized and delocalized pictures consistent. So there are several ways of presenting this. I will show you one here that I think is nice. So let's start with this localized problem. Like in the case of the dynamical mean field theory, or it would be a single site, but here we look at a cluster. In the case of a single site, the problem is so-called an Anderson impurity problem. So in other words, we have interactions U here on the site, and then we have a C of, in the case of the Anderson model, and then of a conduction band, but here it's just non-interacting electrons. So what is the Green's function for this cluster problem? It has a self-energy that is that involves only these 4 sites here in this illustration. And the non-interacting inverse Green's function contains both the Hamiltonian that has not retarded, unretarded direct hopping from one side to the other, and also retarded hoppings here. You can go through this bath and then come back anywhere, if you think in the final picture. So this Green's function is frequency dependent, and this G0 minus 1 includes all these processes. Now, if I want the self-energy, one way to do that is to use the skeleton expansion. And the self-energy, I dropped the R3 piece here. All that you need is this range function to do this skeleton expansion. Now let's go to a delocalized problem. So now I just tile the infinite lattice with these clusters where the self-energy is rather local. And there's a separation here between these clusters. So correspondingly, there's a reduced Brillouin zone that has a wave vector k tilde. And the Green's function for this is this object here. So sigma does not depend on k tilde because it's completely localized here. Now, suppose I want to, again, find the self-energy for this problem. The skeleton expansion is this. All that I need is Gij. And Gij is what? It's just the integral over the reduced Brillouin zone of this Gij that depends on k tilde. Again, the frequency dependence is there. I just didn't include it. So now we have this delocalized picture and the localized picture, and both of them are described by the same skeleton expansion. So it means that this Green's function here that has the self-energy, which is the same as that self-energy, in general, it won't be. I mean, I need to find the correct G0 minus 1. So that's the self-consistency relation. So the delocalized and localized picture becomes self-consistent because these two Green's functions are identical when I find the correct G0 minus 1. So this is the dynamical mean field. So here what I just described is cluster dynamical mean field theory. Now there's another version that's called the dynamical cluster approximation, where the cluster is periodic. And what you do is that you patch the Brillouin zone with self-energy, with you coarse grain if you want the Brillouin zone. So here it would be the coarse graining for a 4x4 cluster. Now another piece of jargon is called impurity solvers. Oh, by the way, if you have questions, you interrupt anytime. So impurity solvers. So one type of impurity solver is to actually do exact diagonalization. Just put a big enough system here, and have these non-interacting sites around that, and do exact diagonalization and write this self-consistency relation. And my colleague is David Sénéchal has a program that will soon be public. Another type of impurity solver is continuous time quantum Monte Carlo. So in that case, what you do is you integrate out the bat of non-interacting electron. It gives you a so-called hybridization function, and that's what enters the G0 minus 1, if you want. This is the action for the cluster. Now, with this continuous time quantum Monte Carlo, what you do is you actually sum the perturbation theory to infinite order with the Monte Carlo method. So there are some subtleties related to ergodicity in the superconducting state that we looked at, and also acceleration, but this basically due to Werner, Millis, and Howley. And there are many now publicly available softwares that do this. I mean, we have our own, but there's publicly available software. My message is just this: here there's no approximation. We find the exact solution within a certain, as usual, uncertainty and statistical uncertainty. And so many people have written this program over many years, not knowing each other and so on. And it's all been benchmarked. And I would say that there's no possible error at this stage. Another impurity solver in the continuous time quantum Monte Carlo approach is the so-called continuous time auxiliary field approach, where this time you expand in powers of U using a Hubbard Stratonowitz transformation to do this. And both of these impurity solvers can be used either with DCA or with CDMFT, but usually DCA, that's the sort of the preferred approach, and there are reviews of these methods. And there are many groups using these methods for the cuprates, and I won't have time or the space to show all the references, but I want you to read some of the names in Europe. I mean, Wu is in China now, and in the USA we have Gold, Millis, Howley, Jarrell, Meyer, Komoto, and in Japan, and there are certainly many more. So I'm going to critique these methods now, so show their weaknesses and their strengths. But if you have any questions, I'll be happy to answer. You have any questions at this stage? It's fine? Okay. So there are pluses and minuses. So the plus is that if you want to describe long-range order, you don't do any mean field factorization on the cluster. The cluster is described by the Hubbard model. But you allow the bat, that are supposed to represent the infinite system, to allow the bat to break the symmetry. And the symmetry breaking can be frequency dependent. I mean, the order parameter, if you want, can be frequency dependent. This is just G0 minus 1.
Maybe I have a naive question, if it's possible.
Yes, please.
Actually, maybe someone else also makes some earlier. Not sure whether someone I'm gonna ask. But my question is naive. The method you described, does that work for a non-relativistic system? Does the method developed also work for relativistic system?
You mean like graphene or something like that? Yes, for sure. Yeah. Yeah, no problem. We've used these methods for actually both for graphene and also for anyway, I don't know why I have a single moment here. Yeah, no problem. Is there any other question? Yeah. While semi-metals, that's what I wanted to say. Yes.
Yeah, I have a couple. At first, what is this bath? Symmetry breaking allowed in the bath.
Okay, so that you know, do you agree? You understand what the bath is now, right? This is just a set of non-interacting, just a set of non-interacting electrons. Okay.
I see.
And that gives a G0 minus 1. But these non-interacting electrons actually, this G0 minus 1 that you choose, you know, by if you take it in action formalism, you're integrating out these electrons here. But the G0 minus 1, you can contain symmetry breaking fields. What I mean is, for example, if you have off-diagonal long-range order, you can have an anomalous part to the self-energy, and that we will use that for superconductivity. So if you think of exact diagonalization, what you do in exact diagonalization is that the non-interacting Hamiltonian that you write, I call it non-interacting, I mean quadratic in fermion operators. The non-interacting Hamiltonian that you write on this lattice contains, let's say, some parameter delta times A up, A down, plus delta dagger times A dagger up, A dagger down. You see what I mean? So this all that we need for this Hamiltonian here is for the back part is that it's quadratic. But being quadratic does not mean you don't break the symmetry, right?
So another question.
Yes.
On the next slide,
yes.
you draw the or then after next. So the localized and delocalized picture. Yes.
Yes.
Is this set of let's say events complete? I mean, if you describe what can possibly happen on localized this lattice and what can happen between these green squares.
Yes. So between the green squares, you just have upping. So the self-energy, if you want, is almost local in the sense that the self-energy, there's a sigma 0, 0, if you want, on this side. Excuse me, there's a sigma 0, 1, a sigma 0, 2, but there's no sigma 0, 3. Okay. Sigma 0, 3 is 0. So that's an approximation.
I see. Approximation. Okay.
Yes. But that's the only approximation. I mean, once you have this problem, you can solve it exactly by computer, but it's still an exact solution.
I see. And is there any reason behind having these squares like 2 by 2 rather than, I don't know, pairs of neighboring sides, or I don't know, triangles or
no, you can choose the cluster as you want. And in fact, I'm going to say in a minute that what you want is see how this behaves as a function of cluster size. Clearly, clearly, when the cluster is infinite, you have the exact solution.
Of course. I see.
Okay.
Thanks.
You see. So, I mean,
André-Marie, on that, can I ask your skeleton graph expansion?
Yes.
That was in the other slide. That seemed to only go to order U square. Oh, it goes to all orders.
Yeah, to all orders. To all orders. You solve this problem.
How do you determine that? How do you determine that to all orders?
By this,
oh, that's the impurity solver. Oh, okay,
that's the impurity solver. Yes.
All right.
Yeah. So the use of this this skeleton expansion is just to show how you can make these two self-consistent. But once you have this problem can be solved exactly with this G0 minus 1. And in fact, then you solve this problem also exactly. You go back to the lattice by including this epsilon of k tilde that represents these hopping here between clusters. Does that answer the question?
Oh, yes, thank you.
Okay. Any other question? Thank you for questions. I mean, it's important. Okay, because I want to convince you of certain things, and the method is important actually. So let's critique the method. So I told you this. So what's included exactly is our short-range dynamical and spatial correlations, and what's missing are long wavelength particle hole and particle-particle fluctuations. Hence, the method is good when the corresponding correlation lengths are small. So when does that happen? Well, it happens at high temperature here. And it happens also at low temperature, right? In the ordered states, the correlation length can be small there. The correlation length is large in this region, and then it becomes not so good approximation. And there are artifacts. Okay, so let's deal with the artifacts.
So, sorry, I have a question. So I was wanted for this part because what I was wondering is what about recovering the spin wave spectrum at zero doping? And I mean, we know these spin waves are very important, right? So when you talk about the correlation length, you're talking about magnetic correlation length or superconducting correlation length?
Both, all correlation.
Okay. And so every time you have long range or nearly long range spin correlations, you will run into problems, right?
Yes, you will run into trouble when this correlation lengths become too large. But it's the same as if you do mean field theory in the classical mean field theory is exactly the same problems, right?
Yeah, but for example, if you do time-dependent Hartree-Fock or mean field, then you recover this spin wave theory spectrum. Whereas, okay, I mean, here is not there.
Yes, but on the other end, you see we have the Mott Insulator here.
Yes.
Okay. And the Mott Insulator has nothing to do with long correlation lengths. That's an important concept. And I will come back to this in a minute, okay? So possible artifacts. So this is a scanning tunneling microscopy by the group of Seamus Davis at doping 0.19 here, and then you change the doping all the way to 6%. And then you do a cluster dynamical mean field theory, and you find that it's quite remarkable agreement for this density of states, and you even have these little bumps here. So you're very happy, these subgap structures, but these subgap structure come from the fact that you have a sort of artificial density weight that you have included here. Okay, so you need to know the limitations of the method. So what to do? Then it's exact in the infinite size limit of the cluster. So you have to compare different cluster sizes, compare real space, CDMFT, and momentum space, DCA clusters. Okay. So let's start with a bird's eye view overview of the zero temperature phase diagram that you get with this this method. So this is for U equals 80, and then these are typical parameters for the cuprates. And there's the order parameter as a function of electron density. So this is the electron dope case and the whole dope case. So without antiferromagnetism, you get D-wave superconductivity like this. And if you include antiferromagnetism, then you get this asymmetry of the phase diagram, and it ends at sort of 95%. And then because of the competition, then superconductivity dies here. Actually, we're missing points here, but it dies. And here there's a coexistence region. So this is in the presence of antiferromagnetism. And as you will see, as I go on in the talk, you will see that we can improve this phase diagram by having larger system. Okay, now let's face the competing ground states. Okay, what do we do with this? So there's a very nice work here, very rigorous, that's done by the Flatiron countries. Flight-Tyron Institute. This is no superconductivity in the pure two-dimensional Hubbard model. And then this other paper, the TJ model, that says that there are many, many states that are very close in energy in this TJ model, which is sort of the large U limit. So I have sort of three answers to this. One is that if you look at the value of the order parameter that they get in this work, there's some error bars, and in fact the order parameters that we find are really small and they are within the error bars of this. The second answer is that there are at zero temperature, you can tweak the Hamiltonian, change a little bit, and then all the details become important. As you raise the temperature, you erase some of the importance of some of the parameters, and also entropy comes in. Okay. So there are these methods can address these competing ground states. For example, if you look at DCA here on cylinders, and you compare with what's found in determinant quantum Monte Carlo, you see that there are some stripy solutions. This is by the group of Thomas Meyer. And a variation of the method I just described as the bond density wave, the wave superconductivity, the pair density wave at zero temperature. I don't want to spend too much time on these competing states that are important, but I would say are not the dominant aspect of the problem.
I'm sorry. I have one question about choosing the clusters.
Yes.
Are you well? You described them as all all of them are theoretically correct. Is it right? They are all complete sets, and you can describe. And do you choose the cluster size for it to just to best fit the observed experimental results?
No. You have to change the cluster size. You have to make it larger. You have to compare different methods, and so and the thing is the limitation of the computers. Really, we can. There's a limit to the size of the problem you can do, and there's this infamous sign problem also with fermions. That's exponential. So that's what limits your abilities. So in other words, if we try, the human brain has some limits, okay, and then there's these nice ideas that are physical ideas that I explained, on why you can do this, and then to do the exact solution. This Anderson impurity problem, we just give it to the computer and it gets the exact result. And then you have to use your judgment to decide, if you believe this or if you need to do something better or something like that. Is that okay?
Yeah, I guess.
That's okay. You can repeat your question differently if I didn't answer correctly.
Well, you just explained that we are looking at the results and we are judging if we believe them, but if all the models describe, if all the size, cluster sizes, cluster figures, they are theoretically correct, they are theoretically complete, and if they are all correct, then they will lead to the same results.
Yes.
Am I correct?
Yes, but the results will be qualitatively the same, but quantitatively different, because you need to change the cluster size. You get the exact result only in the infinite size limit of the cluster. You see what I mean? But already, if the correlation lengths are not too big, then you can start with small clusters, and if the interactions are strong, the self-energy will be local.
And we are choosing all the parameters for the result to better fit the experimental results.
Okay. Yes, that's another point. So if we look at the hopping parameters, I will show you later if I get there. I will show you later. We can get these parameters, the hopping parameter, we can get very good estimates from electronic structure calculation, from band theory. And we also have angle result photo emission spectroscopy that give us, Fermi surfaces, and then we can compare the Fermi surfaces and everything. So I would say that the hopping parameters, they are pretty well known. Okay. Then the only adjustable parameter is the value of the interaction U. Okay. And indeed, for that you need to, if you want quantitative comparisons, you can adjust this parameter U. Is that okay?
Yeah.
Any other question?
Yeah, it's Michel here. I have a question coming back for perhaps to something like, I guess maybe you didn't talk about VCA or this cluster method, but so in the context of local moments, in a problem with local moments, and one might want to do something like, let's say, cluster mean field theory.
I'm having trouble connecting to the internet. Check out the help section in your Ultimate Ears app.
One moment, please.
Okay.
Alexa wanted to have a conversation with me, and I disapproved. So in a cluster mean field theory, so the with short range interactions, only the spins at the boundary of the cluster would experience the mean field, right?
Yes.
And so the cluster decomposition would kind of break the translational symmetry of the problem.
Yes.
And so and then so there are ways or tricks to fix that. So I'm wondering, I guess there are two questions. Is this kind of physics operating here? And if yes, how is it being handled? And if it's not operating, this kind of breaking of translational symmetry, why isn't it operating?
Okay, I'm not sure I understand the question correctly, but the point.
Well, I mean, so you understand the question about the for local moment pictures, right? And for local moments, like let's say an Ising model on some lattice where you would do a cluster mean field theory. There's a problem with that in terms of the interpretation of the solution because of the breaking of translational symmetry.
Yeah.
So I'm wondering what happens to this concern in these methods.
Yes, it's the same. It's the same same concern. But I would say that what's important here is that we can have both this localized and delocalized picture at the same time. So it's a more difficult problem, I would say, than just the spins, right? Because you have additional degrees of freedom. Instead of just having localized spins that do their things, these things can go in and out. And the dynamical mean field takes into account the fact that these electrons can go in and out. And then when you look at the value of the double occupancy on the cluster, for example, then you see that there are local moments. So that's the important thing. We don't have just plane waves or something like that. We have both the delocalized and the localized aspect. That's the strength of these methods. And then as you grow the cluster size, you get more and more of this physics that you're talking about, I think. And in our case, because there's only U, if you want, the spin interaction with the next cluster, this super exchange can in some sense still occur. But if you have in your Hamiltonian, you have an explicit J, then you have to do something that's called extended dynamical mean field, where not only do you have a G0 minus 1 that is self-consistent, but you also have a spin fluctuation operator that is self-consistent. So you have to add layers of self-consistent fields.
I see.
Okay.
Okay, thank you.
So pseudogap. So we had a talk by David Shea that and discussed, and there are many phase transitions here. Now, and that's usually what is meant by T-star. But in reality, if we look at the early experiments, for example, by Alul and Nakano, if you look at the spin susceptibility as a function of temperature, you see that it's not an ordinary metal. A metal would have Pauli susceptibility. Instead, which is independent of temperature, instead you get this loss of spectral weight, if you want, at the Fermi level, that leads to this downfall of the spin susceptibility. So where is this downfall of the spin susceptibility? Well, it occurs here at a much higher temperature than these phase transitions. So we can see that these phase transitions are an instability of the pseudogap state. That's the way I like to see it. And because this is a high temperature phenomenon, that's accessible with small clusters. So let's look at this. Here you have the 12-site cluster by Myers-Calapino, and you see that there is a near half filling. There's this fall, and then as you move away from half filling, then this eventually moves in that direction and eventually disappears. So this is at high temperature, close to the again spin susceptibility function of temperature. So it's high temperature, close to half filling, and then not later. And you see, you can look at the experiment and look at this. And to be completely honest, if you look at the dopings here, they are larger than the dopings here. But I will come back to this later. So 6-site, it still has this jump, this loss of spectral weight. And with 4 sites, I don't show you, but we have the same behavior. So let's compare with experiments. So this is experiments by the group of Taillefer and YBCO. And this is these phase transition business, or at least crossovers measured in transport. And this is for IBCO, this is for neodymium or europium LSCO. And you see that this T-star line is sort of related to the Niel transition here at that filling. It's not quite correct to say that T-Niel is a measure of super exchange, but if we accept this, what do we find? We find that indeed, as we increase U, then this this maximum in the spin susceptibility that I showed you earlier, in this case in 2x2 clusters, has this behavior. In other words, T-star scales like super exchange, and this is related to entropy. I don't want to call that here, but I want to point out that this doping here is called the P-star, and that you see that the fall here is very sharp, like is seen in experiment. But you have to remember that this line here should be above this one. In fact, if you look at the temperature scale, it's sort of obvious. Now, if they in experiment, if they apply pressure, what they find is that this moves this way. I mean, the pseudogap ends earlier. And they have some electronic structure friends that told them that applying pressure on this compound is like reducing the value of second order hopping T prime. And that's what we have here, okay? So T prime equals 0, we get the fall is here. At T prime equals minus 0.3, the fall is there. So as we apply pressure, we reduce T prime and we move this way, and we don't change much of what's happening here, just like what's observed experimentally. And then there's this inequality that was found that P star is less than the doping where you see the Van Hove singularity. And indeed, there's a separation between the Van Hove singularity and P star. And that's quite remarkable here. At T prime equals 0, the Van Hove singularity of the non-interacting system is here. Now interactions have pushed that far away, okay? But it's something that's been seen also by the group of Antoine John.
Andre, quick question. You said that the pressure decreases T prime, right?
Decreases T prime, yeah.
Increases or decreases?
Decreases. Well, I mean, it depends on the sign here. That in absolute value, it decreases it, yes.
So absolute value decreases.
I didn't hear, I'm sorry.
does absolute value decrease or increase?
The absolute value decreases.
Okay, so this is hydrostatic pressure, so it compresses the lattice.
Yes.
So what's the explanation for this? Why would T prime decrease?
It's T prime compared with T always, right? So
is it because just because the atoms are mechanically closer and it is just physically easier to hop to them?
Well,
is
then
this why?
It's in units of T, right? I mean, everything is in units of hopping. Well, I mean, this comes out from the electronic structure, and I haven't thought about that. So, but I think it's a detail for now, right?
It's a very counterintuitive. That's why I was asking.
Well, the pressure is hydrostatic, right?
Right. So it should increase every hopping should.
Yeah, it increases every hopping, but the ratio, it's the ratio T prime over T that counts here.
Oh, okay.
Okay, we're always working in units of hopping little t. So yes, I agree with you. I mean, it increases hopping, but it increases the absolute value of the second neighbor hopping doesn't increase as fast.
But then in principle, one should change also U, right?
Yeah, yes, but you see, you need to change U by a large amount here, and yeah, okay. Yes, I don't mean anything quantitative here, okay? I just mean that it goes in the right direction. But yeah, I agree with you that this is just, this by itself is not a big, something you should make too big. Can I move on? Another questions? Okay. Okay, now remember I told you that I want to show you that this, this P star and the fall of the this sudden fall of the maximum in the spin susceptibility is related to the Mott transition. Okay, so let me talk a little bit about the Mott transition. I will introduce the concept of a Witham line also. So these are my collaborators, mostly Giovanni here. So now I move at that filling, and I do this cluster dynamical mean field theory for a 2x2 system. And this is the temperature, and this is interaction strength. Okay, and what comes out from these methods? Okay, what comes out is that there's a metal here, and here there's a Mott insulator. In other words, here we have local moments, and we are at half filling, so it's really, if U is sufficiently large, we get to the Heisenberg model. If U is not so large and there's additional frustration, we have spin liquids. Anyway, we don't care about too much about the details, except that it's a Mott insulator here. And there's a thermodynamic first order transition by this dashed line. And these two lines are spinodals. In other words, the metal here has a metastable region here, and then it has no choice. It goes to the Mott insulator. And conversely, the Mott insulator can be stable until it reaches this line, then it goes to the metal. There's a critical point at the end of this first order transition, and there's the so-called Witham line. That's something that's known in the theory of classical phase transition, and we introduced this concept for electronic correlated electron problem. So here what happens is that in this region, double occupancy, the average expectation of up and down has a jump. Here it has an inflection point. Okay. So now you tell me, okay, this is ridiculous because we are looking at half filling, nearest neighbor hopping for this problem. So we know the ground state is an anti-ferromagnet. And you're right. So if we look at as a function of U, there's a dynamical mean field phase transition here. And what we are explaining here with this Mott transition is why does it go down here, actually, right? It's because we have this T square over U. It's because we have an insulator here. So if we come from here, why does it become an antiferromagnet? Because the antiferromagnet has lower potential energy. And here, why does it become an antiferromagnet? Because the antiferromagnet has lower kinetic energy. Okay, so this normal state, ground state, even though it's not the true fixed point or the true phase, I mean, it influences what happens with this phase. And this is just about what I was telling you about the origin of this. So let us not lose sight of our objective. So I want to see what happens in the pseudogap. So I start at U equals 6 here, and now we move as a function of doping, okay? So what you find as a function of doping is that, not doping, let's start with chemical potential. So chemical potential. So here you are in the Mott gap, okay? So as I change the chemical potential in the Mott gap, the filling remains equal to 1. Then I go to this metallic phase. It is compressible, clearly. And here it's T prime equals 0, so the same occurs on this side. And then there is a jump to another metallic state. So there's a transition between two metallic states. I claim this is the pseudo gap, and this is the metal. So I guess this plot I've been showing for about 10 years, and there is indeed a problem. I mean, it's, people say, okay, it's an artifact of cluster dynamical mean field. It's an artifact of 2 by 2. Well, it can still tell us something about what happens in the high temperature phase in the same way as I was describing earlier. But let's then see why I say it's a pseudo gap. So this is now looking as a function of doping and temperature. And here, this is the line of where the susceptibility falls, okay? And this is the Witham line of this first order transition. So here, when we look at the statistics of the plaquette states, there are lots of singlets. And here it's more like metallic. And you see why this line ends suddenly. It's because it's a precursor of this Witham line. And this Witham line, lots of things happen that I want to describe. One of them is that the compressibility becomes large. That's quite surprising in a large repulsion. So, and it does not occur in one dimension as we expect. So that's the Witham line. That's what I would call the Sordi transition, and that's the T star I was describing. So to show that this is indeed not just an artifact of cluster dynamical mean field theory or the 2 by 2 system, let's move to another system. It's an isotropic triangular lattice where there won't be this, the antiferromagnetism at high temperature will not be a problem, okay, because it's a frustrated lattice. In fact, I will take the limit T prime equals to T. So there are still singlets, but no possibility of antiferromagnetism at large temperature. Okay, now not only do I change the lattice, but I change the method. I use DCA, and I take 6 patches. So it's a larger cluster, and it's another method. It's another lattice. And what do we see? Filling as a function of chemical potential. We see the Mott plateau. We see this what I call the pseudo gap, and let's look at the corresponding densities of states. If I take a state here, I get a metal. If I take a state here and I look at the density of states, you see this is what I call pseudo gap. And here the yellow star is an insulator, and then I have another pseudo gap, and I go to a metal. And now what happens if I go to higher temperature? At higher temperature, well, I won't see this anymore. And you see that this is starting to disappear. Conversely, if I go to lower temperature, this moves to larger doping. and to lower temperature. When it's at large doping, it's at lower temperature. Okay. So now what I take is a cut at constant temperature, and I plot U as a function of doping for this triangular lattice with DCA and 6 patches. And this is what I was showing you earlier. Okay, so you see the Mott Insulator. So what are the colors? The colors are just the derivative of n with respect to mu. So here we have 0. So it means that this is the Mott gap. And here, when we go down quickly here, there's the compressibility increases, and until it becomes blue. So that's a large compressibility, and that's when we in the limit where we get an inflection point. But the critical point here now is here on this side, and on this side, on the electron dope side, is further away. So I don't want to go through all the details of this thing. Every little gray dot here is a calculation. So lots of calculations here. And the Mott transition is this here. We are at half filling, and as a function of U, you get UC1, UC2, and these are this is the coexistence region for the Mott transition that I described. And the Sordi transition is clearly continuously connected to that Mott transition. Okay, so this pseudogap physics is directly connected to what happens at that filling. So this was shown by Giovanni in the square lattice in 2x2 CDMFT, and the same occurs for this DCA with n equals 6. I have more to say. If you look again at this type is the square lattice. If you just shift the chemical potential here, you can overlap all these curves, with the different values of U, difference of the values of temperature. All that happens is that the transition comes in later or not, but they superpose. Now, if I change the cluster shape, I go to a larger cluster, what happens is this changes a little bit. But for this other cluster, again, there's this so-called, in some sense, some universality. You lose it if you have large changes in T prime. But my point is that it looks like some sort of topological stability, in the sense that if I change the cluster shape and size and so on, then the number of allowed singlets will change, okay? So I get a slightly different curve. But for a given cluster size, this is universal, and it seems to persist for larger clusters, okay? Now, in other words, what I'm showing you is another Fermi surface reconstruction without symmetry breaking. It was a paper by Subir. Now, oh my God, time is going back. Any question? So to summarize, what I showed you is that this rapid fall of the maximum in the spin susceptibility is related to the fact that there's a first order transition that's connected to the Mott transition. And David has a question.
Hi, André-Marie. I just want to ask if you can comment on providing a bit of physical insight into what the pseudogap, how I should think about what is the pseudogap.
In this picture, it's just a lot of singlets. So if you look at, again, the statistics of the cluster states that you find in this quantum Monte Carlo, in this hybridization expansion, you find that 80%, for example, at low temperature, 80% of the weight, of the statistical weight, is into this, this singlet state where you have a singlet here and singlet there, and they resonate. That's for the 2x2 cluster. Now, if you look at the metallic state, completely different. In the metallic state, you have the singlet, you have triplets, you have doublets, you have all these states as the equal weight. Okay.
Yeah, just a quick follow-up question. So does this also explain the momentum dependence of the pseudogap so that it's sort of.
Yes. If you, I could show you at the end, but I have plots of the momentum dependence. Yes, and that works for electron and for all dope. Yeah.
So I want to ask a question. So what you showed is very, very low doping, less than 5%.
Yes, I'll show you what happened.
That's not what we usually call pseudogap. That would be in the antiferromagnetic ordered phase. So it looks like you're above the antiferromagnetic transition then.
No, I will show you. I will show you in a moment larger values of U and larger values of doping. Okay. But if to see the first order nature of the transition and connect it to the Mott transition, we need to be in this regime, because the critical point of the first order transition goes down with U very quickly. It goes down in temperature very quickly. It moves to larger doping and goes down in temperature until it becomes presumably a quantum critical point or some ordinary critical point, but at so low temperature you cannot make the difference. Is that clear?
Yeah. Okay.
Can I repeat this?
No, go ahead. Yeah, because right. But so far it's very low doping.
So far it's low doping, yes. So here you see, okay, the specific heat. Okay, so this is the specific heat. So the specific heat divided by temperature as a function of temperature. So that's the specific heat goes like T log T. Okay, and in this case, for this value of U equals 9. I've already showed you other values with T prime and with U, it moves to larger doping. For this value of T prime and this value of U, then the critical point is here. It's around 12 and 14%. So 12% you get, and 14 and 16, they sort of superpose this T log T behavior. Unfortunately, the experiments of, well, I don't know, unfortunately for us, but the experiments of Louis are in the Taillefer group are at like 10 degrees and 10 degrees Kelvin and lower, and that's the lowest temperature we can reach. So this would fan out at lower temperature, and this here would keep going. And if you increase doping, it turns out there's a Van Hove singularity, as I explained. That's also a T log T behavior. So that's why here you have they go one above the other. And as you increase U, then this goes increase doping. I'm sorry, this goes back to being more flat, which is what you would expect for Fermi liquid. Now let's talk about superconductivity. So the cartoon BCS weak coupling picture, I won't go into, I mean, instead of exchanging phonons, you can exchange spin waves, and that comes from a long time ago. And if you look at the work of Mark Jarrell, Meyer, and so on various cluster sizes, and a small value of U here, doping 10%. So this is the regime where you expect this exchange of long wavelength spin waves to be important. And if they plot 1 over the pair correlation function, they find that it goes to 0, which means that the pair correlation function diverges at some value, finite value of temperature. So this shows that this weak coupling formalism works with clusters up to 26 sites here, and you see that there's convergence. And now there's a strong coupling picture. So you go back to J, you do a mean field factorization, and then you get some D-wave possibilities. And that's due to Varma, Schmidt-Rank, and so on. And what happens in this with these methods? So this is the superconducting transition temperature for DCA with 8 sites, U equals 6, T prime equals 0 by Gould and Millis. And this is Meyer-Scalapino. And so the clear difference between these two is that as you increase the cluster size from 8 to 12 here, you see that you move this transition to finite doping. And you see that it looks more like a dome. And the reason is clearly that long wavelength phase fluctuations come in. I mean, that's the Emery-Kibelson suggestion. Okay, and we can check that in 2x2 clusters. You see in the 2x2 clusters, you don't get this dome shape. You get more this sort of mean field like picture. But if you compute the superfluid stiffness and use the Kosterlitz-Taulis criterion, you find that indeed this becomes more curved. So I'm not showing this, but we have data for this. What I want to show here is a little bit different. If you are for a U that's less than the U for the Mott transition, the superconductivity, so this is doping, this is temperature, and this is the superconducting transition temperature. The color is just the value of the order parameter, so don't worry about the color. You see that the maximum here is sort of at precisely where U and the bandwidth are comparable, right? So at U equals 16, you see that it has gone down. And in fact, it's clearly that the TC goes like J in this model. And but there are many experiments that suggest that there's a pair, there are pairs that form between T star and TC. And basically, this is what you find here in this model. Hank has a question.
Yeah, I have two questions. One of them might be a little bit silly. So the first one is about comparing cluster sizes in your CD-MFT computations. For example, if I were, is it right to sort of interpret the self-energy in each cluster as sort of, you know, you have all these correlations that takes into account the correlations of electrons in all the sites of the cluster, like or rather scattering.
I'm not sure I understand the question correctly.
Like the sigma ij and all the indices.
Sigma ij, yeah. Sigma ij takes into account the interaction within the cluster.
Yes.
But in a mean field, a dynamical mean field that includes all the other electrons. So it allows the electrons to go in and out of that cluster.
Oh, so that's also in the self-energy.
Yes, absolutely. Okay. Very important. Yes. Think of the Anderson impurity problem. Then the rest of the lattice is in G0 minus 1 or G0.
Okay, so my question is like then, let's say you do a cluster computation on a 4x4 cluster, and then you want to compare it to like half the size, right? For example, 2x2 cluster. Wouldn't that implementation also force you to take into account like intercluster in the 2x2 case?
Yes. Yes. I mean, the two results will be different in general. If you're at high temperature, they're identical. Okay. If you're in the ground state, or I mean, at very low temperature where the correlation net is small, they're very similar. But I showed you, right? I showed you right here that they're different at high temperature. Okay, you see here there's a dome, but it's like this, and here for 12 sites, it is moved away, and then for 4 sites, then it's quite different. But if you sort of look at the superfluid stiffness, and you see that it becomes very small as you go towards half filling. At half filling, it's an insulator. The phase fluctuations are huge. I mean, there's number is the right quantum number.
So I guess there would be like a whole ladder of consistency conditions to check if you want to compare like different cluster sizes.
What do you mean by a ladder?
For example, if you because this might be incorrect, but the way I understand how you relate the G's, the green functions in the localized and the delocalized picture is that you have a you pick a cluster size and you go to a delocalized picture and then you compute G in the reduced Brougham zone.
Yes.
But then without, you make an approximation where you say that you don't take into account the intercluster self-energy.
Yes.
Yes. So my question is, if you don't make that approximation at that level, right? Let's say you take into account intercluster maybe one more step, right? Then you will have to reduce your Brougham zone another step. And then
yes, as you increase the cluster size, the reduced Brillouin zone becomes smaller and smaller. Yes, obviously. Yes.
Right. Okay. Another question is, I think maybe I'm incorrect on this, but like we know that it's a superconducting state when you have like a pairing correlation. You computed the pairing correlation, I believe, right? And you got the transition temperature. I was just wondering, like, because you have, I think there are also PDW, right? The pairing density wave.
Yes.
Yeah. So maybe have you computed other quantities that might distinguish superconductivity and PDW?
Yeah, the PDW and superconductivity, I showed you results at the beginning where my colleague has done these comparisons for the ground state, but nobody, to my knowledge, has looked at the function of temperature.
Ah, okay.
Okay.
Thank you.
And at very high temperature, I don't need to talk about any broken symmetry. Yeah?
Mm-hmm.
It's just the correlation length is small and so on. And to answer Patrick questions about the doping, the point of the triangular lattice was to show that this transition exists in a situation where you don't need to worry about antiferromagnetism.
Mm-hmm.
Okay.
Okay.
So, so the phase diagram here is we have this this pseudogap, and we have this Witham line and everything. And here I compare it's again these two other calculations with larger clusters. Now let's increase the value of U. Okay, well that's what I had in the previous slide, and you see that we move here to something else. Then what I plot here is the potential and the kinetic energy, and in this region, the condensation energy comes from kinetic energy. I mean, you gain kinetic energy, and here you gain potential energy. And the point is that this change between these two limits comes in where you have this Witham line. So here I cannot go at low enough temperature to see any first order transition or anything, but I see the Witham line. So I know that there is this transition below, and it has some influence on superconductivity. Like in the antiferromagnetic case, it tells me why it becomes superconducting. Is it because I gain potential or because I gain kinetic energy? See? So the experiments were done by Bontemps, Santander, and Van der Marel by looking at some rules in optical conductivity, and they see something like this. Now, again, to look at Patrick's question. So this is what I showed you earlier. So indeed, you saw this first order transition at very small doping, but this is U equals 6. You see, as you go to U equals 7, U equals 9, you see that it moves to larger doping. Okay, so this phenomenon of whether it's kinetic or potential energy is related to this first order transition that's connected to the Mott transition. Okay, so what is the clue? Okay, in the case of the electron phonon case, just Eliashberg or BCS superconductivity, there are two peaks in the imaginary part of the self-energy that are related to peaks in the phonon spectrum. Okay, so this is frequency and this is this imaginary part. So here we can do the same, and we look at the imaginary part of the anomalous self-energy. There are two peaks, and we look at the imaginary part of the local spin susceptibility, and you see that the peaks, I mean, if we translate this down here, you see that the peaks match. And if we look at the overdope region, here these are experimental results for the where is the maximum chi double prime as a function of onset temperature, which is here is a measure of doping in some sense. I mean, doping is here. We are in the overdope region. You see that the maximum goes down in frequency. I mean, this is a frequency scale. This is the location in frequency of the maximum. And you see that's what happens here. And if you look at if you look again at neutron scattering, and you look at now at this peak, this is in the superconducting state. And if you go to the normal state, that moves this way. And this is, if we look at this high energy peak, when we go in the normal state in red here, that's also what happens. So here, this shows that the glue is this kind of a right? So I have 10 minutes for the 3-band model. Any questions before I go to the 3-band model?
And you can take your time, so don't worry about the time.
Okay. So the 3-band model is the Emery, Varma, Schmidt-Rink, Abrahams model. Okay, these are the references. And I will explain what this model is in more detail in a second. This was done with my student and David Seneschal's student, Siddhartha. And I'm just flashing something that looks like something you have already seen with this first order transition, the pseudo-gap line where the spin susceptibility goes down and the insulator, and the origin of the condensation energy for the superconducting phase that's shown with this orange line here. Okay. So just to show you that, it looks like the 1-band model, but let's look into a little bit more detail here in superconductivity. So what is this 3-band model? Well, the real system has oxygen, and then we want to look at it in more detail. So there is a hopping between the oxygen and the copper, it's the TPD, and then between oxygen and oxygen, that's called TPP. And then there is a going directly, to 4s electron, but that's irrelevant here. We go from TPP prime in between these two. And then there's a site energy epsilon D, a site energy epsilon P, and there's a repulsion U, and there's an orgy of parameters, and you think you'll never get out of this. Okay, so I'll come back on these parameters. But for the moment, let's see what we can do just with some set of parameters that I will call the ionic limiting case that has a manageable sign problem. Okay, so we start with the Monte Carlo. Okay, what is this? This is the density of states, and you see the lower Hubbard band. The blue are copper character. So the density of states is mainly on copper. Oxygen is green. So here, this is called the charge transfer band. You see, it's mostly oxygen. There's not much copper character here. And this is the upper Hubbard band that has both copper and oxygen, but mostly copper. And this is the so-called Zhang-Rice singlet band that I will describe in a little bit more detail. And that's the charge transfer band. And that's what I will call the charge transfer gap. It will play an important role in a second. Okay. So the experimental result I want to look at here is an experimental puzzle that's been around for a long time with oxygen. So this paper is 2016, but in fact, it takes data that, basically at the beginning of the ITC field. So there are different families here. There's the lanthanum family, and there's the bismuth, mercury, thallium type, and this is TC here on that in that scale. The height here is TC, and these are the YBCO compounds. Okay, and now there are two axes because there are two types of atoms. There's the oxygen, that's called oxygen hole content, 2Np, and this is the copper hole content that I call ND. Okay, so now look at that filling here. I can be at that filling if I have 5 electrons now in my unit cell. Okay, because there are 3 atoms, so I can put 6 electrons. If I have 5, I'm at that filling as far as the Hubbard model is concerned. Now along this line here, I get ND plus 2NP is equal to 6. So to 5. I'm sorry. That's the half-fill case. Okay, and then I look at some other doping. So there are several values of ND and NP that give the same doping. And the point of this plot is that you see that for a given doping here, I have different families of superconductors, right? And they have different TC. So what is the dominant effect? The dominant effect seems to be the oxygen hole content. Okay, if I have a large, for a same doping, if I have more holes on the oxygen, I get a higher TC. I get a family with a higher TC. Is that clear? That plot can be confusing. Okay, so now we do calculation. So, you know, to model the different families, we just change the microscopic parameters. And the point is that we get basically the same correlation. It's not precisely the same in the sense that there are some exceptions, but roughly we get the same correlation. Now it's plotted backward. We have ND here and 2NP. So let me flip this around. Now we have the same axis, 2NP and D. It's harder to see that the brown is in front of the blue, but it is. Okay, there's a problem here is that we're looking at a very small part of the phase diagram, but that's the rule of the sign problem. We cannot do better. So let's go to zero temperature with another model that I will call the covalent case, which is actually closer to experiment. So here, the model here, we have the large epsilon P minus epsilon D. So there's a large site energy difference between the P and the D electron. So that's the lower Hubbard band. Here you see is mostly, as I showed earlier, is mostly copper. But here, when the epsilon P minus epsilon D is smaller, you see that it becomes all mixed up a little bit here. So I call it covalent because epsilon P minus epsilon D is smaller. So they are almost at the same level. So they're more likely to have a covalent bond. And they're the same features.
Quick question. What are the units?
Pardon me?
What are the units?
Oh, thank you. So the units are this. So TPP is equal to 1 here. Okay. And I will show you that in electron volt in the next slide. You didn't want to see this, huh? Okay, so we have all these parameters, and there's this very nice electronic structure calculation by Weber, Hawley, Cotillard with state-of-the-art band structures. And okay, TPP that I took equal to 1. Here we can see it. So TPP is this hopping. You can see this value in electron volts, and you see that if you change the compound, it doesn't change very much, okay? It stays around 0.6. So that's why we take this equal to 1, because we can always go, for any given compound you give me, I can always go back to the electron volts. Now, okay, so now look at the TPD here. So it varies again, but not that much. But epsilon P minus epsilon D varies also more, okay, from 2.61 here, 1.24 here, but and then we have TPP prime that is small here. It's 0.1 compared to 0.6 here. That's our unit. Forget about this. I mean, that's something else. So the parameters I'm going to show you are the ones for this compound: bismuth, strontium, calcium, copper, oxygen. So we have two models now. We have this ionic model that is that I will show always with fill circles, and we have this covalent case that I will show with these open circles. And now what I want to explain, remember, is the fact that the TC seems to be larger when I have a larger hole content. Okay, so let's look at this model with its where the parameters are basically taken from band structures, except for the values of U, which is a fitting parameter here. But I mean, there are all sorts of reasons you can compare with all sorts of experiments and see the ballpark for this U. So we get U equals 12. So that's our reference model, right? When I was showing here, this is our reference model. U equals 12. This is this covalent model, and the ionic model is this. Okay. Now the point is that I can, mimic the fact that I change the values of the parameters, within that range that I showed you here, the epsilon p minus epsilon d for the real values. And you can see that the domes indeed go to have larger optimal doping when they have a larger oxygen hole content. Well, that's wrong here. I mean, I increase the oxygen hole content and it goes down in this purple region. Why is that? Well, in this purple region, the charge transfer gap closes. Okay, so charge transfer gap is important. Now, what am I plotting? I'm plotting for the covalent case, where parameters vary within this reasonable range that we saw from this table. You can see these are what is plotted here are the optimal doping values. You can see sort of the domes as the shadows here in the back. And this was the closing of the charge transfer gap. And this is the ionic model. Okay, the optimal. So the ionic model, this is another limiting case, has always smaller optimal parameter than the covalent case. So, okay, look at this. This is again the maximum order parameter, but now I plotted like experimentalists do all the time as a function of total hole doping. Look at this, completely crazy. I mean, there's no relation, right? Here you get some very nice correlation, but here, I mean, okay. You give me total hole doping, the order parameter can be this, it can be that, it can be anything, okay? Now, another experimental puzzle. The TC, or the TC or TC maximum, so the optimal value of TC. And here is plotted the charge transfer gap. Okay, the experimental charge transfer gap I showed you on this, well, it's a theoretical plot, but this corresponds to the experimental charge transfer gap. And what you see is an anti-correlation, okay? So when the charge transfer gap closes, the TC goes to, closes, the TC goes to 0, that's in this region. But if you increase the charge transfer gap, TC goes down. So what do we get? This is the covalent model. This was this closing of the charge transfer gap. But suppose you have a charge transfer gap, as you increase it, the order parameter goes down. This is for the covalent model. If you go to the ionic model, you have this. So there was this paper by Weber. I'm almost done. So thank you for your patience. Weber, Guy, Hawley, Cotillard. They showed here the TC as a function of epsilon D minus epsilon P. So that's not the charge transfer gap. It's a microscopic parameter. And there are many microscopic parameters that you need to fit to have a given charge transfer gap. But nevertheless, you see there's this anti-correlation, that TC goes down when the charge transfer gap increases. So if you plot this, again, the maximum order parameter, but this time as a function of the charge transfer gap in dimensionless units, in other words, as a function of total bandwidth, you see now that there's sort of a perfect correlation for the covalent model and for the ionic model. But the ionic model is always lower than the covalent model. So these two facts actually are not independent. If you plot the optimal hole content here, so the value of the hole content at optimal doping as a function of the charge transfer gap, you see that the two are basically correlated in both the ionic and the covalent model. And all that means is that when you have a smaller charge transfer gap, when you dope in the oxygen band. So it's related to the value of the charge transfer gap. So there are more holes with a smaller charge transfer gap. There are more holes on the oxygen. Okay, so it all comes together. It's only one and the same phenomenon. And we can, I won't go into details here. We can see which of the microscopic parameters are more influenced. And then there's a covalency. Okay, this is in the talk by Chandra Varma. And there was this statement that what's special about copper is that this affinity energy, what is plotted here is the affinity energy of the first row transition metal in relation to the ionization energy of oxygen. And copper is special because there's this correspondence. In other words, I think that what we have also shown is that the covalency is better than the ionic model. What about Cooper pairing mechanism? Well, let me pause for questions. I mean, I'm going really fast here, but that will be my last topic here. No question? Okay, Cooper pairing mechanism. This is chi double prime, so the imaginary part of the spin susceptibility at pi as a function of frequency. So you see the blue is as a large peak here. And the other ones are not so important. Now what's plotted in black here is 1,000 times the order parameter. So, okay, but why do I have a frequency dependent thing here? It's because if you take this integral from 0 to omega of the imaginary part of the Gurkov function, of the retarded value, I mean, here is the imaginary time expression, but here, if you take the integral to infinity, what you get is the equal time, C up, C down. So that's what I call the order parameter. So at large frequency here, we have the equal time curve. But you see that as a function of frequency, this builds up. So there's some retardation, and then there's an overshoot, and then if we look at the one band model, it has the same type of thing. Now, let's look at larger clusters. Okay, so when we take the beta salpeter point of view, so what this means is that you start from the normal state now, and what you do is you look at this equation for this called linearized Eliashberg equation. This is the particle-particle scattering vertex. And you write this as an eigenvalue problem. And you find the largest value. When this value is equal to 1, you go to superconducting. Okay. So you look at the largest value of this lambda, and it tells you what state you are going to. Okay. So these are results, again, by the Meyer group that I put here upstairs. And you see that, in fact, they have the same problem. So they're looking at the ionic model. But my point is that they get D-wave. Okay. And if you look at the one band model, it's D-wave. And this is the Zhang-Rice singlet. It's just the fact that what you should be looking at really is this molecular orbital. So let me summarize and conclude. So I think that I showed you what's intrinsic to the dope Mott insulator is that there's a pseudogap. On our first order transitions that you see, at affilling, the Mott transition. And then you see at the finite doping, that is a Sordi transition that's continuously connected. And that can give rise to a quantum critical point if you go to large values of U. There's D-wave superconductivity that's mediated by short-range spin fluctuations. And I showed you that we understand actually almost quantitatively the role of the charge transfer gap and the oxygen-hole doping. There are other objections that you could have. I mean, that the fact that we neglected nearest neighbor Coulomb repulsion, but in fact, we have some papers that look at that and show that it's no problem. There are recent experiments that are consistent with the dope Mott insulator picture. And I was supposed to talk about entanglement properties, but I won't do that since it's very late. But the upshot of that is that sharp variation of the entanglement-related properties and not broken symmetry phases characterize the onset of the pseudogap at finite temperature. So my question to you is, what is the most important problem from your point of view? What is the smoking gun calculation that the group of people that is working on this problem could do that would, convince you that we have at least a handle on this problem? So the floor is open. You have lots of smoking guns in the United States, so it's a dark joke. Okay, so you can write to me. So I would say that we move from the lone genius approach using this herd immunity idea to the herd genius. I think this is really a collective effort that we're all doing towards solving this problem. And so I thank you for your patience with me. So yeah, any more questions?
Thanks, Andrew, for a very great talk. Yeah, anyone has a question? Maybe I can ask a question first. So in your calculation, it seems you show that the pseudogap regime expands with when we increase the Hubbard U. Is that correct?
Yes, yes, absolutely. Yes.
Oh yeah, but then I'm confused because you also have a slide saying that the T star is proportional to J, which is inverse of U. So
yes, yes.
But how are these two pictures consistent?
Yes, I mean, I showed you that the TC goes down when U is too large. So you don't need a huge value of U to to move away. And in fact, if we go to this 3-band model, we get much more realistic values of the doping where things happen. What am I doing here? Just a second. Okay. I have too many things on my screen now. That's a big mistake I just did. Okay. Yeah. So yeah. So that's my answer is that you don't want to. I showed you the maximum TC that we get is sort of in this intermediate regime, but it doesn't mean that the ITC have the largest value of TC that can be attained, right? There's some value of U and some value of J, and the value of U is or the orders that I showed you that give the J experimentally. The J is what 1,300 millivolts, no, degrees Kelvin, 113 millivolts or something. So yeah, this is the value of J you need to work with. I mean, at that filling, you have the spin waves that tells you you have that tells you the value of J you should be working on, and you have the hopping parameters from electronic structure calculation. So basically, you have the value of U and J that are relevant to the real materials.
Yeah, sorry, Professor Tremblay. I have one question related to the last slide. You're saying what are the pressing questions or smoking gun signature? So my question is related to a very important expression experimentally deduced, which is related to the proportionality constant between the coefficient of the linear resistivity and the value of TC. So these two quantities are proportional to each other. A is proportional to TC. So my question is whether there is any progress using cluster dynamical mean field theory in the deduction of this expression theoretically, because experimentally it is well established.
Yes, yes. So, well, one thing I can say is that if you look at the color plots that I had with this, but sorry for you will get dizzy here. Then you see that the maximum in TC is in the region where the scattering rate. I mean, the color here is about the scattering rate. So that's the imaginary part of the self-energy. And you see that the maximum occurs where the imaginary part of the self-energy is largest. So that partly answers your question. Now, transport quantities are very often accessible experimentally. But as you know, for theorists, it's a nightmare because there's a problem of vertex corrections and so on. But we are working on this actually, and yeah, more to come. more to come soon. So that's okay. That's one other calculation that would help convince you. But there's already a partial answer here.
Okay, thank you.
And in fact, the linear resistivity at high temperature is easy to obtain. The problem is to go to low temperature and keep it going linear. And that's what we are working on. Yes. Any other question?
I have a question. You showed this very nice first order liquid-liquid or metal-metal phase transition.
Yes.
And there is a miscibility gap there, right? In some
yes.
And I saw that TC often coincides with the critical point also around
yes.
there. So what do you expect to, I mean, do you expect this miscibility gap to be cured by superconductivity, or what happens around there?
So you see in this, what I plot here is the normal state results. So except for this green points, but the point is that once you have superconductivity, this first order transition disappears in this one band model. It turns out in the 3-band model, there are still some transitions, and there are some experiments that suggest that. I mean, by Sakuto, for example, with Raman scattering. But at least in the 1-band model, once you go into the superconducting state, what's left of this first order transition is this crossover from kinetic energy dominated condensation energy to potential energy condensation dominated condensation energy. So, and in that case, it's just a crossover. But if you remove the superconductivity, you see the first order transition in the normal state. You see?
So if you remove superconductivity, you would expect to see like a phase separation or some inhomogeneities. So there is somehow competition between inhomogeneities and uniform superconductivity.
Yes, in some ways. Although, I mean, you understand that, as I was explaining earlier, you know, the true ground state here of this. Okay, let me step back a little bit. Look at superfluid at helium-3, okay? Helium-3, we know the ground state is superfluid. And we know the normal state is very well described by Fermi liquid, okay? But so, and what is Fermi liquid based on? It's based on the ground state that is Fermi liquid, okay? So even if you have the wrong ground state at finite temperature, you can describe things pretty well. Okay, so this normal state with this first order transition is most probably not the right ground state. But if you go at finite temperature, you see all these crossovers, then they describe the true normal state. And now the superfluid, the superconducting state and everything keeps traces of this this normal state, but in other words, if you think in renormalization group language, this normal state that I'm describing with the first order transition that's connected to the Mott transition and everything, this ground state is not the true fixed point of the system. But what I'm claiming is that the true fixed point of the system is very close to that. So if you go down in temperature, you're controlled by this normal state fixed point. And then at the last minute, whoops, you go to the other one. Okay. And as usual, I mean, in the long range order phases like superconductivity and antiferromagnetism, they cure some divergences of the normal state. So here is the same thing.
Okay. Thank you.
Other questions?
Yeah. Thank you for the very interesting talk. I have a question regarding the implementation, or rather the applicability of these cluster methods. So do we need to assume a certain property of the lattice in order to implement the methods, like lattice symmetry, ordered periodicity, stuff like that?
Yes, in that case, definitely we assume that there is a periodicity. On the other hand, there are methods to treat disorder as well.
I see. Mm-hmm.
So
Okay,
to treat the disorder, basically, you have to, it's as if, you know, every cluster that you will look at will be in a different environment, okay, that contains the disorder.
Mm-hmm.
And and you have to use statistics and so on. So, but there's the Vlad Dobroslavievich, for example, and Gabi Kotliar have worked a lot on these methods. So yeah, it can be generalized to disordered systems. And as usual for disordered systems, you're just adding another layer of complexity, but that may be very relevant for the real problem cases. Yes.
Yeah, that's cool. Thank you.
Other questions? Okay, and if not, well, thank you very much for your patience. I appreciate all your questions and everything. If you have more questions, if you have more suggestions, just write to me. I'll be happy to discuss. And as I say, I mean, we see here Doug, which is really a pioneer in this, and so many people. As I say, I think it's a collective effort we are doing on this. I mean, there were some key ideas at the beginning, and then you just need an army of people that really grind this down and make it work.
Thank you very much, Andrew.
Thank you. Thank you very much.
Thank you very much for joining.
Bye.